In Outbound Architecture Stage 1, we talked about the foundation, suborbital flight, the proving ground, the first rung of the ladder. If you haven't watched that one, it's worth your time before this one, because what we're about to discuss sits directly on top of everything Stage 1 gives you. Stage 2 is low Earth orbit, and it is not a small step up from Stage 1. And it is a categorically different undertaking, different physics, different duration, different systems requirements, different economics, different everything, and except the underlying discipline, which carries over intact. If Stage 1 is where you learn to build the ladder, Stage 2 is where you discover how tall the ladder actually needs to be. Let's get into it. The physics first. In Stage 1, the job was vertical. Get up, come back down. The velocity required to reach the edge of space, defined at the Kármán line, 100 kilometers up, is modest by orbital standards. A suborbital vehicle needs enough thrust to punch through the atmosphere and coast to altitude. What it does not need is the velocity to stay there. That distinction is everything. Low Earth orbit begins at roughly 160 kilometers and extends to about 2,000 kilometers altitude, but altitude is almost a distraction. The thing that defines orbital flight isn't how high you go, it's how fast you go sideways. To maintain a stable orbit at LEO altitudes, a vehicle must travel at approximately 7.8 kilometers per second. That's roughly 17,500 miles per hour, fast enough that the curve of Earth falls away beneath you at the same rate you're falling toward it. You're not fighting gravity. You're falling around the planet in a continuous arc. Getting to that velocity from zero requires an enormous amount of energy, far more than a suborbital arc. And that energy requirement cascades through every design decision your engineering team makes. More propellant, more structure to contain it, more thermal protection for re-entry because you're coming back in from orbital velocity rather than the comparatively gentle return of a suborbital arc. A vehicle returning from LEO hits the atmosphere at speeds that generate temperatures exceeding 1,600 degrees Celsius. That's not an engineering footnote. That's a dominant design driver. So right out of the gate, before you've touched a single system beyond propulsion and structure, the LEO vehicle is fundamentally harder than its suborbital predecessor. And that's before you've addressed the problem that actually defines human spaceflight in LEO duration, the duration problem. A suborbital mission lasts minutes. The highest profile New Shepard flights ran about 11 minutes from launch to landing. In that time, your crew experiences microgravity briefly, your life support systems carry a minimal load, your thermal systems manage one transit through the atmosphere, and your crew is back on the ground before most of the failure modes you've engineered against have had time to assert themselves. LEO changes that by orders of magnitude. The shortest crewed LEO missions in history, Vostok 1, Yuri Gagarin's single orbit in 1961, lasted 108 minutes. The typical ISS rotation today runs 6 months. Some crews have gone longer. The human body, it turns out, has a great deal to say about extended microgravity exposure, and very little of it is positive. Bone density decreases, muscle mass atrophies, cardiovascular systems adapt to the absence of gravity in ways that cause problems when you come back. Vision can be affected by fluid shifts in the skull. The immune system behaves differently. Circadian rhythms are disrupted. The ISS sees 16 sunrises and 16 sunsets per day. Radiation exposure at LEO altitudes above most of Earth's protective atmosphere is meaningfully higher than on the ground. None of these are showstoppers. The ISS has hosted humans continuously since November 2000. We have accumulated an enormous body of knowledge about how to keep people alive and functional in that environment. Countermeasures exist. Exercise protocols, nutrition management, pharmaceutical interventions, careful mission planning. But every one of those countermeasures is an engineering and operational system that has to be designed, built, tested, validated, and maintained. This is what the duration problem looks like when you actually work it. It is not one problem. It is dozens of interlocking problems, each of which has to be solved, and each solution of which creates new requirements elsewhere in the system. That's systems engineering at its most demanding. And it's one of the reasons the early government programs spent years and billions just learning how to keep humans alive for increasingly long missions before committing to destinations beyond LEO. How we got here, the government era. Let's be clear about what the government programs accomplished because the record deserves straight treatment. Mercury put Americans in orbit. John Glenn's Friendship 7 mission in February 1962, 3 orbits, 4 hours and 55 minutes, proved that a human being could function in orbital flight and return safely. That was not assumed. It was demonstrated at substantial risk by people willing to strap themselves to rockets that had a documented tendency to explode. The courage involved was not small, and the engineering achievement was not either. Gemini extended the duration, added rendezvous and docking capability, and gave NASA the operational experience it needed to plan Apollo. It was the bridge program, the one that took the fundamental capability Mercury had established and turned it into a mature operational discipline. Spacewalks, long duration missions, precision orbital mechanics. Gemini was where NASA learned to fly in space rather than merely survive it. Apollo required a leap beyond LEO entirely, which we'll address in future stages, but the program's legacy for LEO operations was significant, and the engineering, the systems philosophy, the operational culture, all of it flowed from the discipline that Mercury and Gemini had built. On the Soviet side, Vostok and Voskhod established early milestones, including the first spacewalk by Alexei Leonov in 1965, and Soyuz became the most reliable crewed orbital vehicle in history. It is still flying. Think about that. A spacecraft design conceived in the 1960s is still the backup crew vehicle for the International Space Station in 2026, still launching, still returning crews safely. The Soyuz program is a testament to what ruthless engineering conservatism and iterative improvement over 60 years can produce. Skylab, the American space station program of the early 1970s, demonstrated long-duration operations in a way Mercury and Gemini could not. Crews of 3 lived and worked aboard for up to 84 days, a record that stood for years. The data collected on human physiology and extended microgravity directly informed every LEO program that followed. And then there is the Space Shuttle and the International Space Station, the largest and most complex engineering project ever completed in orbit, built by 16 nations over more than a decade of assembly flights continuously crewed since 2000 and scheduled for deorbit around the end of this decade. The ISS is 109 meters wide, has a habitable volume of 915 cubic meters, and has hosted 274 people from 21 countries over its operational life. It is extraordinary by any measure. It was also extraordinarily expensive. The ISS program has cost somewhere between $150 and $200 billion, depending on how you count it. The shuttle, which served as the primary assembly vehicle, cost roughly $1.6 billion per flight in fully loaded operational costs. That's not a sustainable economics for what comes next. And the government era knew it, which is why the commercial crew and commercial cargo programs were born, a deliberate decision to hand the operational tier of LEO access to industry and let NASA focus on the frontier. That handoff was the right call, and it's bearing fruit right now. The commercial revolution in LEO. The story of how SpaceX was born and how it changed the economics of orbital access could fill several videos on its own. The short version. Elon Musk decided that the fundamental reason space was expensive was that rockets were thrown away after every flight, and that fixing that problem was worth betting the company on. He was right. Falcon 9 is now the most flown orbital rocket in history. Its first stage has been reflown more than 20 times on individual boosters. The cost to orbit has dropped by an order of magnitude from the shuttle era. And the Crew Dragon capsule, which restored American crewed access to LEO in 2020 after a 9-year gap following shuttle retirement, is a fully commercial vehicle built by a private company, operated on a service contract. NASA buys seats. SpaceX runs the vehicle. That model, government as customer, industry as operator, is the template for everything that follows. And it's being applied right now to the next layer of LEO infrastructure, the stations. The commercial station landscape in 2026 is active and competitive, though not without turbulence. Vast's Haven 1, a single module station the size of a large shipping container, is now targeting Q1 2027 for launch aboard a Falcon 9 after delays pushed it from its original 2026 target. It will host up to 4 commercial astronauts for short duration missions and is explicitly designed as a stepping stone to the larger Haven 2 architecture. Axiom Space is taking a different path, attaching its first module to the ISS itself, planned for 2026 before eventually detaching into a free flying station. Axiom has already flown 4 private astronaut missions to the ISS and is the most operationally experienced of the commercial station competitors. Starlab, the Voyager Space and Airbus joint venture, completed a critical NASA review earlier this year, clearing it for fabrication, testing, and assembly with launch targeting 2029. Blue Origin and Sierra Space's Orbital Reef rounds out the major competitors aiming for late-decade operations. But the commercial station landscape got more complicated in March 2026, when newly confirmed NASA Administrator Jared Isaacman held his ignition event and floated a dramatically different approach. Concerned that a viable commercial market doesn't yet exist to support fully independent stations, NASA proposed potentially funding a government module that private companies could attach to, rather than backing fully free-flying commercial platforms from the outset. That proposal generated significant industry pushback, and as of now, NASA has signaled it will keep the commercial LEO destinations program as currently structured. Government as customer, not as builder. The debate itself is instructive. It shows exactly what the transition from government to commercial operations looks like in real time. Messy, contested, subject to revision, but moving in the right direction. The commercial model doesn't arrive fully formed. It arrives through exactly this kind of friction. The broader financial picture for commercial LEO is changing in ways that matter. Voyager Space became the first modern space station enterprise to go public in June 2025, raising roughly $383 million with a market capitalization near $3.8 billion at debut. That is not speculative money chasing a concept. That is institutional capital pricing orbital infrastructure as a long-duration growth asset. The space station business is becoming investable. When that happens, when the capital markets decide a sector is real, the pace of development changes. We know what LEO actually has to deliver. Let's talk about what Stage 2 is actually for, because commercial space station is a phrase that can obscure as much as it reveals. The ISS has generated enormous scientific value: materials, science, biology, medicine, physics, atmospheric research. Experiments conducted in microgravity produce results that ground-based labs cannot replicate, because gravity on Earth is a constant that distorts certain processes in ways you can't control for. The microgravity environment of LEO lets you run those experiments cleanly. That research value is real, and it will continue on commercial stations. But the commercial case for LEO goes further than research. In-space manufacturing is the next frontier. Certain materials, fiber optic cables of extraordinary purity, protein crystals for pharmaceutical research, semiconductor structures, can be produced in microgravity with characteristics impossible to achieve on the ground. Vast's Haven 1 lab is already nearing full capacity with payload partners including Redwire, Uri Gravity, and Interstellar Lab, targeting exactly this in-space manufacturing market. The manufacturing case for LEO is not theoretical. It's being built into the first commercial stations right now. Private astronaut access, space tourism at the orbital level, is the third market pillar. Axiom has already demonstrated this works with 4 private astronaut missions to the ISS. The price point is high, tens of millions of dollars per seat, but the market exists, and as vehicle costs continue to fall, that price will come down. The question is not whether people will pay to go to orbit. They already are. The question is what the price needs to reach before the addressable market expands meaningfully. And then there's the market we haven't fully conceived of yet. Every new infrastructure tier in human history has generated economic activity that its builders didn't anticipate. The railroads created industries that didn't exist before the railroads. The internet created industries that didn't exist before the internet. What LEO infrastructure creates, beyond what we can currently see, is one of the genuinely interesting open questions of the next several decades, from LEO to what's next. Stage two is not the destination. It is, like stage one, a capability layer, infrastructure that makes the stages above it possible and sustainable. The vehicles that achieve and sustain LEO operations become the workhorses for cislunar logistics. The life support systems that accumulate years of flight hours in LEO get extended for the longer durations of deep space missions. The commercial operators who build their businesses in Earth orbit look outward for the next market because that's what commercial operators do. SpaceX's Starship is the machine that embodies that transition most clearly. It is designed for LEO. It is designed beyond LEO, lunar surface Mars further. Its economics are built on the same reusability logic that Falcon 9 proved applied at a scale that makes deep space operations commercially viable in a way they have never been before. Starship is stage two, becoming stage three, becoming everything that follows. The workforce being trained today on commercial LEO missions, the astronauts, the mission controllers, the systems engineers, the operations staff, is the workforce that will operate the cislunar tier. The culture being built in the commercial station programs, the discipline of operating in orbit on a budget that has to balance the operational rigor of sustaining humans far from home, all of it carries forward. LEO is not a waypoint to be cleared and forgotten. It is a permanent tier of human civilization in space. It has to function sustainably, economically, continuously as the frontier moves outward. The ISS proved humans could live in orbit. The commercial programs will prove they can afford to. That's the standard stage two has to meet. And right now, with stations under construction, capital flowing, vehicles flying, and a workforce in development, it is meeting it. No. We are living through the transition from stage one to stage two in real time. The suborbital tier is operational and recalibrating. The orbital tier is commercial and accelerating. The gap between where we are and where we need to be is measurable, visible, and actively being closed. This is not a program waiting for permission. It is a market finding its form. The rung is being built and the ones above it are waiting. Let's get to work.